In this video, we're going to review the basic purpose of hash functions when applied in tandem with RSA. So overall, the goal of this, at least in our limited explanation of how these things work, is going to be to use digital signatures covered in the last video, not just as a way of verifying who the message came from, but also as a way of signing contracts. So to sign contracts. So unfortunately for the first part of this video, using actual numbers to do an example would be a bit too cumbersome because the numbers would be so huge. So we're just going to start with Alice and Bob as usual. And Alice, instead of having actual numbers for her keys, she's going to have so public key EN and private key DN. Now, suppose that Bob sends Alice a contract. So Bob sends Alice a contract C, which is this string. So I owe Bob $100. Now she can sign this in the sense of sign a contract using her private key as follows. So Alice signs C as follows. So first thing she wants to do is convert this contract, this message, into some sort of number that she can then exponentiate using her private key. So first, convert C into a number. Now you need some sort of scheme for doing this. One way that we could do it so that from the number you can still recover the original contract would be to take C and then do some sort of like maybe ASCII conversion into a giant binary number. Then once you have this giant binary number, you're just going to call it M, and you can think of it as being a number in decimal now. And the point is, if you think about each of the characters in this message turning into a binary string with 8 ones and zeros, the resulting number of converting the whole string is going to be absolutely huge. So this is huge. Then what Alice can do, I mean, it's still not too big for her to work with. So what she can do to sign the contract is she then sends M to the D mod N to Bob as her signature. Now, how does this number that she sends to Bob prove that she signed the contract? So let's say that Alice isn't making good on her debt, and Bob has to prove to the authorities that Alice signed that contract. So what he can do is Bob proves Alice signed as follows. What he can do is he takes the number that she sent to him, M to the D, and then he shows everyone her public key, E, and demonstrates that when he takes that power, it gives the message M mod N, which he can then convert back in from a number back into a contract, so undo the conversion. He would take M and he would turn it into a binary number, and then he would interpret it as ASCII, and then he would get the original contract C, which says I owe Bob $100. And the whole point is, this proves that Alice signed because only Alice could have computed the number m to the d, which is exactly the number which, when raised to e, gives back the contract. So only Alice could have provided Bob with the number m to the d. Okay, but now there is a problem, and the problem is that typically contracts are long, and already the numbers that we're working with when we use this scheme right here for changing contracts to numbers, already the numbers are huge, but in practice contracts are longer than I owe Bob $100. So what do you do? So problem, contracts are long. Well, suppose that Bob sends a contract C that's 100 pages. You can't convert it to a number as before, so what you have to do is come up with a function that takes in a very long contract and converts it into a small number. So create a function, let's call it H, that takes a long contract and returns a small number. I mean, small in comparison to our old scheme. So small number. So if C is the contract, what we want is H of C to be small. So, for example, H of C could be something, we'll say something a little bit silly here. It could be the number of vowels in C times the number of consonants in C. That will always be a relatively small number compared to if you converted using ASCII and thought of it as a binary number. So then, for instance, if you did H of I owe Bob $100, that's going to be 4 vowels times 3 consonants, so 12. Then now we can actually use real numbers to show how Alice could sign this contract. So now if Alice had keys, say public key 103 2059, as in one of the previous examples, and private key 647, again 2059, then she would sign the contract by taking H of the contract and signing that number. So she signs by sending H of the contract to the power of her private key, so 12 to the 647, which is 800 mod 2059. She sends that to Bob. Now the point is, the same scheme for Bob proving to the authorities that she signed the contract, that still works. He can take this number to the authorities if Alice sort of goes back on her debt and say, well, look, when I raise this number to the power of Alice's public key, I get back 12, which is H of the contract that she obviously agreed to. But there is a problem. So there's still a problem with this. That argument that Bob just gave also could be used to argue that Alice signed a different contract. So this can make it look like Alice signed. So the original contract was C. Maybe it will look now like she signed C prime, which is I owe Bob $1,000. And how does it look like she signed that? This is because h of C was 12 and h of C prime, where here h is the function that multiplies number of vowels and number of consonants, it's also 12 because adding this extra 0 up there didn't change the value h of C so h of C prime is the same. So this is a problem. And it's only a problem, though, because our function h was very, very simple. It was easy for Bob to come up with a different contract, C prime, that had the same value when plugged into the function h. So you can fix this by just using very, very complicated functions. So to fix this problem, so the problem is fixed in practice. By choosing complicated functions, h. Now, the whole point is there are, in real-world applications, there are contracts, C and C prime, where when you plug them into real hash functions, they will give the same value. But the hash functions are so complicated, the ones that are used in practice, that you can never find such a pair, C and C prime.